Now we'll discuss the Maxwell Boltzmann Distribution Law. Okay. Consider a system of n distinguishable molecules of a gas. Now we know that the Maxwell Boltzmann statistics is a classical case. So the particles are distinguishable, and we consider a system having to left n number of particles, and the particles are distinguishable. Okay. Now the n consists of lots of smaller particles, n1, n2, ni, . Okay, these n1, n2, ni are the constituents of the total system. Okay. Now suppose n1 of them have energy E1, n2 have energy E2, ni have energy Ei, and so on. Thus, the entire assembly of molecules can be divided into different energy states with energies E1, E2, E3, Ei, and having N1, N2, N3, Ni molecules. Now, number 1. The total number of molecules N is constant. See, the system consists of N distinguishable particles, and since the system is not interacting with outside, so the total number of molecules remains constant. N equal N1 plus N2 plus Ni equal constant, and if we differentiate it, the delta N, delta N1 plus delta N2 plus delta Ni equal 0, because the differentiation of a constant is equal to 0. Now if we sum up this then summation I del Ni, so delta Ni equal 0. Question number 1. See, summation I delta Ni equal to 0. If I take first I equal 1, then delta N1, then if I take I equal 2, then delta N2 goes to 0. Similarly, okay. Now this is equation number 1. I come to the point 2. The total energy E of the gas molecules is constant. Okay. Hence, E equal total energy equal E1 N1. N1 molecules have energy E1, okay, and N2 molecules have energy 2, so E2 N2, E3 N3, Ei Ni equal constant. Again, when you take the differentiation, delta E equal E1 delta N1, E2 delta N2, E3 delta N3 plus Ei delta Ni equal to 0. Differentiation of constant equal 0. Again, if we take the summation of this, and then we get summation of Ei delta Ni equal 0. Equation 2. See, if I take I equal 1, then it becomes E1 delta N1, then next E2 delta N2, next E3 delta N3. Similarly, it goes on. Okay. Now, suppose there are Gi cells with energy Ei. The total number of ways in which Ni molecules can Gi cells mean what? This. Suppose I have cells. Gi number of cells with energy Ei. Okay. Now, if I want to distribute the Ni molecules in these energy levels, then how it will distribute, or the possible number of ways, these molecules we can distribute among these cells. Okay. The total number of ways in which Ni molecules can have the energy Ei is Gi to the power Ni. Hence, the total number of ways in which N molecules can be distributed among the various energies is, see, the number of ways Ni molecules can have energy Ei is Gi to the power Ni, and the number of ways in which N molecules, see, this is a capital N, and capital N, we know that capital N equal N1 plus N2 plus N3 N4. Now if we sum up, if we take all of them, then it comes G1 N1, G2 N2, G3 N3, Gi Ni, and this is the W1, the total number of ways in which N molecules can be distributed among the various energies. Okay. Now come. the number of ways in which the groups of n1, n2, n3, ni particles can be chosen from n particles is, now this is the distribution. I have n particles. N particles is n1 plus n2 ni. Now the number of ways in which these particles can be chosen from a total of n particles is n factorial, n1 factorial, n2 factorial, ni factorial. This one. Okay. The number of distinguishable ways in which n molecules can be distributed among the possible energy levels is W equal W1, W2. We know that W1 equal G1 to the power n1, G2 to the power n2, Gi to the power ni, and W2 equal n factorial divided by n1 factorial, n2 factorial, and 3 factorial. Now the quantity W, this one, is called the thermodynamic probability for the system. Okay. For the most probable distribution, W is maximum subject to the restriction that the total number of particles n and the total energy E are constant. Now for the most probable distribution, W is maximum keeping the total number of particles and the total energy constant. Okay. Now if we take